This video gives an overview of all of the different ways of calculating electric fields. The emphasis is on interpretation. There's about a half a dozen different ways of calculating the field, so knowing how to decide which one to use is at least as important, if not more important, than knowing how to use each method. I'll present these in the order of importance for an introductory course like ours, not the order we learn them or the order that you'll eventually probably think of them. Some of the ones towards the bottom are more general and thus more important if you go into a more advanced class. In addition, most of the statements I make assume the fields are static, as is the case at the start of this course. I list this one as 0 because it's not really a method of calculating a field as it is a method of knowing what the field is. If the point is in a conductor, the electric field will be 0 if we've got static fields and static charge distributions. The reason is that charges in the conductor will move under the influence of any force if the field is not 0. So as long as the field is not 0, there'll be a force that will move the charges around until the field is 0 and they come to rest and are in static equilibrium. The important distinction I want to make here is that there's a difference between being in the conductor and inside the conductor. In the conductor means that you're in the metal, in the copper or aluminum material that conducts electricity. The field is 0 there, as shown in these crude sketches. The shaded area is the area where the metal is located. Being inside the conductor means being inside a space that might contain some other charges or might not. In any case, what's going on inside the conductor in those empty areas depends on other things about the rest of the problem, not the presence of the conductor. It might be 0 inside or it might not be, but the field in the conductor will always be 0 if the conductor is in static equilibrium. This example, number 21.7 from our textbook, illustrates this. The field is 0 in the shaded region, which is where there's a conductor, but in that interior region, because of the enclosed charge, the field is not 0, even though we are inside the conductor. This is also not really a method of calculating a field, but the basic principle of superposition. The total field is the vector sum of the fields produced by each source. So once we know that we're not in a conductor, so the field's not necessarily going to be 0, we need to identify each of the sources of the field and use the appropriate method for each one. That is, our interpretation is applied to each individual part of the problem. This is an illustration of that. There's a negative charge at the lower left that produces the blue arrow field E1. There's a line charge, continuous distribution, to the lower right that produces the red arrowed field E2 after you do the integral over that continuous distribution. You do those two separate problems, then add the two vectors to get the total E field at the field point. Now I'm showing two very different methods in one single problem. This is pretty rare in our class, but less rare in more advanced classes at junior-senior level or in real-world problems. Okay, now let's look at each of the methods in turn. If you have a point charge, you just do KQ over R squared R hat, being careful to follow the same definite procedure each time. I expect you to be able to do this for almost any charge location and field point that I would give you in a problem. Always remember to assess your answer. Is the field going away from a plus charge, going towards a minus charge? Second, a charge distribution that has symmetry. Is it a continuous distribution of charge but one with symmetry? If the answer is yes, then use Gauss's law. This is the first of Maxwell's equations and the most common advanced method that we'll encounter. I want you to pay attention to the steps that are described in the IDEA approach for strategy 21.1 and how those steps are modified and adjusted for each of the examples in chapter 21, and notice how I use them in class. You should be able to do or explain the steps used to turn the surface integral E dot dA into the field strength ER times the area A for each symmetry, but I want to emphasize this in red. Your focus should be on the critical thinking needed to determine what is the charge enclosed for a particular distance R, for a particular enclosing surface for any particular problem. Quick overview. The surface integral, it gives you the flux, which is the Q enclosed over epsilon naught. We can reduce that to the field strength times the area for a particular simple situation. Again, equal to the Q enclosed by that surface divided by epsilon naught. For spherical Gaussian surfaces, for spherical symmetry, you'll get the area to be 4 pi r squared. For problems of cylindrical or axial symmetry, the cylindrical area formula is going to give you 2 pi r times the field strength. Notice that there's no formula for Q enclosed. You must add up the charges inside each Gaussian surface of radius r based on the geometry of the problem and the specific details of that problem. You have to think to do these problems. Number 3 is we've got a potential, V of r, measured in volts. If we have this, then the E field in general is the negative gradient of V. That's what that symbol's name means. In general, it's the negative gradient of V, but in our problems, we'll only do one-dimensional problems where the field will be the negative derivative with respect to x of the potential V, and we have to put in by hand the I hat vector to make that derivative of a scalar into a vector electric field. This is also how we measure electric fields in the lab when we measure the voltage difference over some distance delta r, and put in by hand that direction pointing downhill. There's a nice picture of this in our textbook. The electric field points downhill in that potential surface, and that arrow is always perpendicular to the lines of equal potential. If we have a completely arbitrary charge distribution, we have to integrate over the distribution. This is used in more advanced classes, but not really in this one. I expect you to be able to set these up and not necessarily have to do the integral on an exam. We take a little slice, find the differential of charge dq at that point. For a line, it's just lambda of x dx. We then do everything else as if it was a point charge. So the little tiny piece of field is k dq over r squared r hat, where again we'll almost always use r hat to be r vector over r. Once we've got that little piece done, we've got the integrand, and we just have to integrate that differential of E from A to B over the charge distribution, and we'll have the vector field. At that point, you just do calculus. Finally, if you have a time-varying magnetic field, you can also produce an electric field. This is called Faraday's law. It doesn't appear until chapter 27. The important detail is this is definitely not a static field. I'm including it here just for completeness because it is one of the other important methods of finding electric fields. It's quite different from the ones that we do at the beginning of the course. The field circulates around in closed loops. The field vectors are tangent to those circular field lines that go around the region of changing magnetic field. It's quite different from the situation with a fixed static point charge where those fields radiate from a particular point and originate at a charge and end at infinity. If I go back, you see these do not originate anywhere. They originate in space, circulating in closed loops around that changing magnetic field. It's a very different situation than the sorts of things that we look at the start of the course. Finally, there's something way beyond all of that, and that is using Maxwell's equations in their differential form for arbitrary time-varying fields. This method is beyond Calc 3, so even people who've had Calc 3 would not have seen these particular kinds of things. The Maxwell's equations for electric fields are what's called the divergence of E, where the gradient operator is dotted into the electric field, and that's equal to the charge density divided by epsilon naught, where that charge density produces electric fields that diverge from the source field. And the second one is called the curl operator, where you cross the gradient operator into the electric field, and that has as its source the negative of the change in the magnetic field with respect to time. So first, you're going to look at these and say, you don't know what these mean, which of course is why they're not in this course. They're also not in our book. You should also notice that I need to know a lot more than just electric fields and charges. I also have to know about magnetic fields. So these things don't really show up until much, much later in the course. And finally, you have to solve a partial differential equation, in fact, a vector partial differential equation in 4 variables to work with these equations. We'll look at just a taste of one of those because these equations plus the 2 for magnetic fields produce electromagnetic waves. So I'm going to end here with my reference. These come from a bunch of different places in the book and overview from myself.